Hello and welcome to the preliminary design review for the INROS team from the University of Nottingham. Our aim is to offer opportunities for students to experience what it is like to work collaboratively in a team and develop the necessary skills to solve problems. The project is being run as part of the larger effort by the INROS organisation to prepare students for industry by giving them skills they are lacking within the traditional curriculum, namely applying learnt skills, working with multidisciplinary teams, and hands-on skills taking a project through the entire life cycle. The climax of this year's effort is the Violin project, which aims to design and build a vehicle capable of entering Mach 23 and the EUROC. There were several key requirements that constrained the vehicle, the key ones being the target apogee of 3 kilometers and the need to release a 1 kilogram payload. This was additionally challenging as the vehicle was also designed to enter the 9-kilometer category in EUROC, so generating a concept capable of doing this with minimal design alteration between events was highly complex. This complexity was addressed with a TOPSIS analysis, and it was determined that a single one-stage 99.6mm inner diameter glass fiber vehicle was optimal, scoring 29% better than the next best. Due to the EUROC rules and regulations, there were several technologies we wished to demonstrate before that event, which generated motivation behind some of the missions we wished to conduct. The two primary missions of the rocket is to deliver the payload and release it at 3 kilometers, as well as its safe recovery. The secondary missions include technology demonstration. With the vehicle concept and mission outlined, a mission ConOps can be presented. Once the go for launch is given, the vehicle will be powered on and final checks will be carried out before the vehicle is mounted on the launch rail. From here, we will have a holding period until launch, lasting 20 minutes, where our solar power mission will be conducted. At T-1 minute, the remove before launch pin will be taken out, and we will do some final checks from the ground station that all is go for launch. The launch then occurs at T equals 0 seconds when the motor ignites. At T plus 3.83 seconds, the motor burns out and the vehicle is traveling at 274 meters per second. From here, it goes to apogee, which occurs at 3 kilometers. To help achieve this accurately, the vehicle employs air brakes known as the drag raising system, or DRS. At apogee, pyrotechnic charges ignite, which separate the nose cone, deploying the payloads, as well as a 30 centimeter drogue parachute. From here, the vehicle descends at 43 meters per second to 120 meters, where another pyrotechnic charge deploys a 1.8 meter main parachute, bringing the descent velocity to a safe 5.8 meters per second, before landing at T plus 131. The CANSAT then also lands nearby, and transmitted GPS data allows for speedy recovery.
In line with the sustainability Simius provided, the main function of the team payload is to characterize the effectiveness of flaps as an alternative recovery system for CANSAT reuse by measuring landing speed. Another part of the primary function is to implement solar panels on the rocket airframe, which will allow us to test their ability to keep the battery charged pre-launch. The team and outreach payload have now been combined into one CANSAT, therefore the secondary function will be to collect gas composition data, the electronics for which are being made by Ivanhoe School. Based on this concept, the specific payload requirements have been reviewed and further implemented in the mission and system design, and the main ones have been outlined in the slide. The ConOps diagram on the left provides an overview of the payload mission. The sequence of the mission starts on the launch stand, where the solar panels mounted on the rocket airframe will keep the payload battery charged via magnetic connectors, and voltage and current data will be collected and stored. Upon deployment at 3 kilometers, the payload will be deployed from the rocket and detached from the magnetic connectors. Speed data, as well as GPS and altitude data, will be collected as defined by the Mach 23 requirements. This data will be stored on an SD card so that it can be recovered. However, there will also be live telemetry transmitted via radio to the ground station so that the payload can be easily located after it has descended. The flaps will deploy following a signal from the COTS flight computer and spring up to act as a drag device, reducing the landing speed to approximately 8 meters per second.
You can see an overview of our team here. Our supervisor is Dr. Chantel Cappelletti, and we have utilised the full 15-member limit with members from several different disciplines, which addresses the key issue the team faced last year, lack of skill diversity. The team's responsibilities have been broken down into several different subsystems, as outlined here.
Here you can see an annotated 2D diagram of our vehicle. It's comprised of 3 main sections: the lower and upper main body and the nose cone. Starting with the payload, the 3 individual payloads proposed have now been replaced with one payload at the bottom of the payload bay, furthest left on the diagram, with spaces at the top end. At apogee, the upper black powder charge ignites and pressurizes space behind a piston. This piston is pressed up against the payloads that press against the nose cone. This transferred the loads induced by the charge to the nose cone shear pins and ejects the nose and drogue. The drogue chute will then pull out the piston and subsequently the payload. This system protects the payloads from charging gas and heat. The main parachute is located below the avionics bay and will deploy below 200 meters. This will be more simply deployed by a black powder charge directly pressurizing the parachute bay and separating the airframe. These will both be attached to strong point bulkheads at either end of the avionics bay. As part of the payloads, solar panels will be mounted to the airframe externally. This will be achieved by creating a groove in the upper main body so they sit flush on the airframe surface and sealing epoxy. The fins will be mounted onto the vehicle using external fin can with separate fin mounting. This has been done to allow for the fins to be modular and easily swapped out. It also enables the fins to be easily replaced if they're damaged. Shear pins secure the section of the vehicle together and are designed to break after firing of the pyro charges. A baffle exists between the payloads and the pyrotechnic charge to mitigate damage while still transferring the force required to separate the nose cone through the payloads. Finally, the thrust from the motor will be transferred to the vehicle through the thrust bulkheads in the lower main body tube and directly in compression from the avionics tube to the upper body and then through the payloads to the nose cone.
The avionics bay is responsible for housing key electrical components that govern the rocket's flight control. With it being the anchor point at which both the drogue and main parachute attaches to, it is imperative that the structure is well designed in order to withstand the high loads that occur during parachute deployment. The way we've combated this is by threading 3 steel rods going through the internal structure of the avionics bay. This will be attached to the top and bottom bulkheads screwed in tension. This allows the transfer of external forces through the steel rods rather than directly through mounted PCBs. I will now pass it over to my colleague Dan, who will talk more about the key electronics within the avionics.
So the avionics systems are being completed as a final year MEng electronics project by myself. There will be 4 PCBs on board the rocket, which will be held in place with 3D printed mounts. There will also be 2 batteries, 1 single cell LiPo for the low voltage circuitry and 1 2-cell Li-on for the pyrotechnic channels and the 5-volt circuitry. This 2-battery design should help avoid brownouts when the pyro channels draw a large current. If you look at the diagram on the left, in the grey box is the main avionics board. It's also seen in the 3D model. This contains the sensors, the GPS and the transceiver, which I'll talk more about in a second. In the green box is the camera board. This controls camera activation and stores camera data. The orange box contains the drag raising system board. This controls the DRS, which again we'll talk more about in a second. The blue box in the bottom left corner is the COT system. This will be an egg timer proton and will control the pyro channels. While the main avionics board has this functionality, to remove the student-built avionics, the COT system will have full control and the main avionics board will not be connected to the pyro channels. This board will also send its own data to the MAB to be stored and compared to onboard data for more accurate results. The safety brake in this system completely disconnects the battery from the pyrotechnic channels until we're fully prepared for launch. The main avionics board transceiver will transmit at 868 MHz with a duty cycle of less than 1% to comply with European and now UK regulations. The charging umbilical will provide power right up until the moment of launch and will ensure the batteries are fully charged at the time of launch and will be balanced to avoid brownouts and voltage spikes and means the electronics will be powered for the maximum of time allowed by the batteries. The control system, which we'll talk more about on the next slide, is implemented on a board with actuator control in the form of a stepper motor driver and stepper and servo driver circuitry. In the welcome presentation, there was a worry about this system activated during motor burn. To ensure this doesn't happen, air start functionality of the COT system will activate a latching circuit which will apply power to the DRSB. While the control systems themselves originate from student-built avionics, no power will go to this board and the DRS will not be active until a COT system allows.
The static stability of the rocket will remain between 2.5 and 1.5 calibers throughout active flight prior to apogee. The vehicle will utilize a modifiable ballast bay near the engine to control the center of gravity to ensure that it is constrained to a maximum stability of 2.5 or less while retaining an apogee roughly 30 meters greater than 3 kilometers. In the vehicle's apogee control, the drag raising system or DRS will employ fins that will be actuated to extend axially out from the rocket body using a PD controller. The further these fins extend, the more they will reduce the static stability of the vehicle, as it will shift the center of pressure up the rocket body towards the center of gravity. Initial estimates of this effect have been done using OpenRocket. However, OpenRocket lacks the capability to accurately measure the effects that fins which have a large streamwise cross-section have on the performance of a rocket, which is what these DRS fins are. Therefore, this is a very preliminary simulation, and further simulations will be run using more robust methods, such as CFD, once the design has reached a more stable point.
Based on expected rocket performance, calculations were performed to roughly estimate the amount of drag the system needs to produce. It was determined that the rocket diameter was sufficiently large to allow for internally stacked fins, deploying perpendicularly to the rocket body axis, as you can see in the diagram. It is critical that on loss of power or signal, the system has a failsafe to close the fins. This will be ensured through the mechanism design. A single electric motor will turn a torsion spring loaded gear. If the motor fails, the fins will be returned to their safe position by the spring, complying with the failsafe. Using just a single gear will ensure that all the fins deploy together. The fins will be under severe loads as they deploy, which will be taken into account during detailed design to ensure that they are sufficiently supported and are able to retract in case of loss of signal or power.
The motor selection, as usual, presented a major challenge due to stocking issues. We were unable to source any motors between 2,600 and 3,600 Newton-seconds impulse, which was ideal for our mass breakdown, with our required diameter to fit 98mm motors for Euroc. Due to this, we selected the smallest available above the ideal and have made considerations for very thickness bulkheads to increase mass as well as change inertia properties. This also allows us to alter mass to aim directly for 3 kilometers if the DRS cannot be used. These factors led us to the Cesaroni Pro 75 L995P. This was massed to aim just over 3 kilometers, allowing the DRS system to reduce this during flight. This recently became more challenging as our ideal supplier, Eurospace Technology, unlisted 75mm 3-grain cases. However, on contacting them, they plan to get them back in stock, and additionally, Malcolm Rockets has one in stock.
The control system will be based around the error between the altitude of the rocket and the required altitude, along with its derivative. Simulation software has been developed using MATLAB to simulate the rocket's trajectory, which has been compared to OpenRocket, and a graph showing the two simulations can be seen on the left. This MATLAB code will be used to simulate the control system with the DRS, allowing us to find the best coefficients for a PD controller. Further plans include using data from CFD simulations, wind tunnel testing, and potential test launches to improve the software to get more accurate simulations for the DRS control system.
Having evaluated a range of manufacturing processes for the major components of the rocket, we have settled for the above. The body tube will be manufactured through a filament winding process by Collins Aerospace. Additional grooves and notches will be machined by Collins too, ensuring tight tolerances as they act as coupling tubes, so they need to be precise. GFRP has been chosen primarily due to its radio transparency over CFRP, as well as its cost and weight too. The bulkheads will be manufactured in-house using machined aluminium. These will be manufactured using conventional machining. The fins, couplers, and nose cone will be SLS 3D printed out of nylon 12, with potential for either nylon 12 GF or a resin substitute. Similar to our Mach 22 entry, they will be infused with epoxy to enhance their structural properties, as well as surface finish. The internal avionics structure will be manufactured via a mixture of FDM and grayscale resin 3D prints, and potentially composite resins. The internal support structures will also be SLS 3D printed out of nylon 12.
This block diagram outlines the components that make up the payload avionics, showing both connections for power in red and black and for communications with the microcontroller. The sensing systems are based on the mission outline, and sensors include an altimeter, accelerometer, current and voltage sensors, as well as the GPS, which will provide live location data. The power source for the payload is a single battery, with secondary power coming from the solar panel. A power budget was created for the payload, and a drain time of 3 hours was used to select an appropriate battery capacity. While this capacity will be ample for this mission, and the solar panels may not be required, the voltage and current sensors allow us to determine if the solar panels would be a suitable solution for charging for future launches, where the wait time may be much longer.
The external payload structure is made out of phalonic tubes from Black Cat rocketry, with the coupling tube protecting the avionics and the body tube being cut into 4 sections acting as the flaps. These flaps will flap up via spring hinges after they are signaled to deploy and slow the payload for a safe recovery. The internal structure has been designed to fit 2 avionics systems, one being the team avionics and the other being the outreach avionics. A bulkhead will be used to separate the 2. Rods will run the entire length of the payload for a robust structure. The avionics will be mounted on these rods running down the length of the inner payload casing, and metal bulkheads will close off the structure at each end. An eye-bolt and parachute housing have also been included into the payload design, so that a streamer can be added if required. Stacking of CANSATs for the future launches has also been considered in the design, with notches around the circumference of the top and bottom faces.
The payload design is robust, with high-strength materials and support structures in place. Load cases allow us to understand the forces acting on the payload and design for them. The main ones can be seen in the table. The load from the piston will need to be transferred to the nose cone. 25 Gs of acceleration will be withstood. The flaps need to withstand drag forces. Shock loads occur when the flaps open and landing must be survived. To test that the payload can survive these loads, hand calculations, FEA and drop tests will be carried out.
As mentioned, the recovery device for the payload is the flap system. It hasn't been represented in the model, but flexible plastic will also be connected between the flaps, increasing the reference area. Calculations have been carried out to predict the behavior of the payload descent depending on the recovery system configuration and timing. To avoid drift beyond a 1.5 kilometer radius, flaps will not deploy immediately, but will deploy upon descent at 100 to 200 meters above the ground and will slow the landing speed to approximately 8 meters per second. The flaps will be held by a fishing wire, which will melt following a signal from the onboard COTS computer, allowing them to flap up to deployed position.
The payload will transmit recovery data at 2.4 GHz, so as not to interfere with the 868 MHz the vehicle recovery data will be transmitted at. This means the ground station will have 2 transceivers and 2 antennas to receive data from both the main vehicle and the payload. The ground station will output live data to the ground station app with a data output and a GUI. The ground station will be inside a waterproof container to be impervious to the elements, with a basic LCD display to display the basic required recovery information, such as the GPS coordinates for both payload and vehicle, to allow for easy recovery in case weather prevents the full GS app being used. A basic mock-up of this app GUI can be seen on the right-hand side. The data will be stored in 3 locations, one on board the vehicle. This is expected to be the most reliable. The ground station itself will store all transmitted data as a backup in case of failure and recovery, and once within the app for analysis during flight.
The systems engineering approach to this project follows the V model shown. We started with the project's objectives evaluation. We have 148 requirements from both competition's guidelines and defining our own constraints. From these requirements, many concepts were formulated and were compared using weighted decision matrices to down-select the ideal design. We have completed the decomposition and definition phase, having defined interfaces between subsystems and parts, which we use to generate a design failure mode and effects analysis. We are now moving on to designing and building parts for the CDR. Our preliminary mass breakdown, shown on the right, has a total mass of 11.4 kilograms. The largest contributors are the motor, ballast, and fuselage in a current model, though the ballast mass is very likely to reduce as the model is refined. This table shows the main risks at the launch event and our mitigations in place. The main risks to be considered are the major changes being made to the Europe guidelines. Now, this may require significant changes to the design, and it would be too late to implement them before Mach 23. Therefore, accommodations may be made later after the Mach 23 launch event due to the time constraints. The launch vehicle may exceed Mach 1, so ballast can be used to reduce the maximum velocity if simulations suggest that the flight will be supersonic. A test flight will hopefully be conducted to verify simulations before the launch event.
Here the budget is presented. We would like to thank the UON CARO team who we made a grant application to, which we won and got £14,100 through their grant application. This has made the vehicle development as well as the attendance to Mach 23 and the UROC possible. Additionally, £3,500 has been provided by the faculty, but this has primarily been directed towards other INROS projects. You can see the cost breakdown of Mach 23 on the right, with a total of £5,174. However, we actually expect this to come down as we have overestimated various systems for leeway. Here you can see the project Gantt chart. Prior to the PDR, we had the initial outline design, where we received feedback on our conceptual design. After the PDR, a round of procurement will be conducted and some manufacture of well-defined components will take place while we are still working on detailed design of other systems. Soon following the CDR will be a final round of procurement, which will allow final AITV to take place prior to the FRR. We wish to do a test launch before Mach 23, and the most suitable event for this would be MRC on the 14th of May. However, this was only 2 days after the FRR, and ideally feedback from that would be provided before the test launch. We would like to discuss this further. The test launch will be a stripped down launch vehicle only, employing the essential subsystem. That will then provide a month and a half to correct any issues and finalize testing and integration for the Mach 23 event. We've used a very powerful template for our work breakdown tracking. With almost 400 deliverables, it's quite beefy, but with the organizational tools available, it's become a lot more manageable. You can see here the work package tracking. The PDR is only at 74%, but the remaining tasks under that are in progress to an almost finished state, so we are not concerned.
Reviews. Our focus this year has been to develop relationships with companies. We have reached out to Collins and RS, who are we are in conversation with, taking part in their grassroots skills workshop. We are in the process of organising an event with Ivanhoe Primary School, where they will build part of our CANSAT. The main objective of this event is to inspire young people and show them what a career in engineering entails. We're also working to attend Women in Engineering events, where our members will give talks and encourage a diverse range of people to take part in our projects.
Finally, we just hosted our FlatSat workshops that gave members of INROS teams the opportunity to get some hands-on experience with electronics typical of spacecraft. We attached some management documents in appendix with the submission, and we thank you for your time. Please let us know if you have any questions.